Hi guys, hope you're doing okay. Sorry it's been a little while since I posted anything. Still trying to figure out, you know, if this is really working, if this is helpful, if we're able to make progress this way. I'm not a huge fan of this virtual learning. I don't like not getting to see you guys and interact and figure out what we're learning and have conversations and things, but doing the best we can with the circumstance. So hopefully we'll have some more information shortly about how the rest of the year is going to progress. Um, but until then, we keep on plugging along. So um, I'm trying to, if I recall correctly, the last thing that I talked about in my previous video was skeletal structures. So hopefully those are coming together okay for you. You're kind of getting the hang of drawing those simpler versions of larger organic molecules. But today we need to talk about polar bonds, and this is a topic that we cover in Chem 2, but we need to reiterate it here because it becomes pretty important, particularly when we start looking at reactions. That will be for a little while, but a polar bond, well, recall if you will, a bond, right, and we're talking primarily here about covalent bonds, exist between atoms that are sharing their electrons in order to complete their octets. Okay, generally speaking, these are going to be bonds formed between nonmetals. Right? A polar bond is a pair of electrons that is being shared unequally. Okay, so you can almost think of the covalent bond as kind of this tug of war. As long as both sides of the bond, meaning both atoms, are of equal strength, then the bond is shared evenly. But if one of those atoms is stronger than the other, has a greater pull on those electrons, then the bond becomes polar. They become shared unequally. Well, what determines how strong a particular atom is? It's the electronegativity. Okay. So essentially, electronegativity is the ability of an atom to attract bonded electrons. And so some atoms have a larger nucleus, they've got more protons, they've got less nuclear shielding, and so they are better able to attract electrons than other nuclei. The electronegativity is actually listed on your periodic table. If you have that laminated copy, if you flip it over to the back, there's a big chart there. It's the biggest chart of all the elements, and I believe it's the third or fourth column of that chart at the top. It says En. That stands for electronegatividity. Now, I will give you a small caveat. I don't actually agree with a lot of the electronegativities that are on there. I've picked out probably 4 or 5 of them that are not accurate, and so we'll have to make some adjustments once, if and when we get back. But we'll figure that out as we go along here. But you will see the electronegativities of various elements listed out. And yes, there's a unique electronegativity for every element. Okay. So anytime you have a difference of more than 0.4 in electronegativity between two bonded atoms, you're going to have a polar bond. Okay. So let's look at a few examples of that with a few different molecules here. So the first one, right, it's a Lewis structure. Actually, all of these are Lewis structures we've seen a couple times. Formaldehyde. So we've got 3 different atoms. We've got carbon in the middle there. Carbon has an electronegativity of 2.5. Oxygen has an electronegativity of 3.5. And hydrogen has an electronegativity of 2.1. Okay? So again, anytime you have a difference in electronegativity of more than 0.4 between the two atoms, you have a polar bond. So recognize the difference between carbon and oxygen is 1 in terms of electronegativity, and so that carbon-oxygen bond is going to be polar. At the same time, the carbon-hydrogen bonds, there's a difference of 0.4, and so that's a non-polar bond. It's not greater than 0.4. So that's an important one to know. Carbon-hydrogen bonds are non-polar. Okay, the electrons between them are essentially shared evenly. Yeah, carbon's a little more electronegative, but not much. Okay, and so that's a nonpolar bond. Okay. Also, if we go over here to this example, anytime you have an atom that is bonded to itself, right, there's no difference in electronegativity at all. So this carbon-carbon bond is also nonpolar, in addition to all the carbon-hydrogen bonds being nonpolar. Down in this last one, again, we've got a carbon-hydrogen bond that we know is nonpolar. Nitrogen has an electronegativity of 3.0, and so here we've got a difference in electronegativity of 0.5, and so that is a polar bond. Okay? So the way that you're going to do this is to use that table on the back, and if any of those numbers don't agree with any of the ones that I've presented, change them. Hydrogen is 2.1, carbon is 2.5, oxygen is 3.5, nitrogen is 3.0. Those are probably the most common ones that we run into in organic chemistry. There are a few others that we probably should talk about at some point, but I'll say that. Unfortunately, I don't have a copy of that periodic table with me here, so I'm not sure exactly what needs to be fixed on it off the top of my head. But maybe I can find a copy and make those corrections for you. We'll do that in a later video. So once we've identified a polar bond, a difference of more than 0.4 in terms of electronegativity, there are two ways that we can go about identifying it in a molecular structure, okay, or in a Lewis structure, either way. Okay, the first is called a dipole moment. Okay, so a dipole moment is nothing more than an arrow that shows the direction in which electrons in the bond are being pulled. So in this case, oxygen is the more electronegative atom. It does a better job of attracting electrons, and so the electrons in that bond are going to be pulled towards the oxygen. Right? On the other side, you'll notice that the tail of this arrow kind of looks like a little plus sign. Well, that's because electrons are being pulled away from carbon. Negative charge is being pulled away, which makes this carbon appear a little bit positive. Okay. We don't draw dipole moments for the carbon-hydrogen bonds because those are nonpolar bonds. Right? Over here in our other structure, nitrogen is more electronegative, and so we're going to draw a dipole moment. The dipole moment is going to be drawn right along the bond itself. And it doesn't matter if it's a double or a triple or a single bond, right? It's really just the interaction between those two atoms. So nitrogen being more electronegative is going to pull the electrons in these bonds towards itself, and it's going to leave that carbon just a little bit positive, and so you see the tail there that looks sort of like a plus sign. Okay? So that's a dipole moment. The other way that we can represent this is using what are called partial charges. Okay? So partial charges are going to indicate the partial charge of the atoms involved in a polar bond. Okay, so partial, the symbol for partial is the lowercase Greek letter delta. Kind of looks like a closed S on the bottom there. And so oxygen, because it's pulling the electrons towards itself, is going to be partially negative charge. And because those electrons are being pulled away from the carbon, that carbon is going to be partially positive. Okay? And again, we don't have to write anything for the hydrogen because that's the bond between carbon and hydrogen is nonpolar. On the other side, over here, because the electrons are being pulled towards the more electronegative nitrogen, that's going to make the nitrogen partially negative. And because those negative electrons are being pulled away from the carbon, that's going to leave the carbon partially positive. Okay? So another way to say that is that this nitrogen is electron rich and this carbon is electron deficient, okay, because it's partially positive. That becomes really important when we're talking about reactions, understanding where the partial negatives and partial positives are in a chemical reaction. If you'll recall, one of the first things that I told you guys is that something like 90% of chemistry can be explained by the idea that negative chases positive. And so if you can come to that realization, you start to realize that where reactions occur is really dependent on where things are electron rich and electron deficient. Okay? And that's something we'll talk about a lot more as we get into reactions a little bit later in the term. So what I would like you to do with this, I'd like you to practice. And so at some point I gave you a sheet of Lewis structures. I've given you several at this point. What I'd like you to go through, pick one, pick two, however much practice you think you need. This is kind of independent time to a large extent. So, but I'd like you to pick some Lewis structures, and I would like you to practice identifying polar bonds. using both dipole moments, that's the arrow, and partial charges. Okay, so take a look at that. Guys, if you need anything, I know I still haven't heard from very many of you. A couple of you checked in with me. I appreciate that. If you get a chance, send me a quick email. Let me know what's going on. If there's some way that I can help you, please let me know, and I can do my best to aid in whatever's going on. So, all right, guys, stay safe, stay healthy. Hope to talk to you soon.